I'll talk about how the idea of smart contracts came about, and I'll talk about some of the blockchain technology and what makes it secure. But I'll probably skip through the blockchain technology part pretty quick, because I assume everyone was at Martin's talk. And then I'll talk about Ethereum and how Ethereum uses the blockchain as a state machine, and how to build decentralized applications on Ethereum. Okay, so to start out with, why do we want to build smart contracts? And I'll start with a little bit of intro to crypto anarchy. And I know the idea of crypto anarchy sounds sort of negative, because it sounds like we want to overthrow the government or something. But that's not really what we're trying to do when it comes to crypto anarchy. What we want to do is be able to create and enforce our own rules without having someone in charge to enforce the rules for us. For example, like living in whatever country you live in, there are laws and there are police and there's an army to make sure you follow the rules. But we want to create a system where we don't need that. We don't need the cops, we don't need the courts, we don't need the president or whoever to tell us what the rules are and make us follow them. The reason for that is because having a third party be in charge of the rules, that might not be trustworthy. For example, if you were selling candy, you can have a person stand in front of the candy and sell it for you, but then you don't know if that person will steal some of your money or give away the candy for free. On the other hand, if you use a vending machine instead of a person, the vending machine will for the most part, be fairly reliable and always dispense the same candy for the same amount of money. The other reason why we want to create our own rules is we want to disintermediate financial authority. We're going to be using our own currency that isn't controlled by any one state. Because when you use currency that's been issued by a central bank, then you have to follow the rules of that particular government. So we're doing peer-to-peer transactions. We want to set the rules and enforce the rules for what transactions we do. And finally, or most importantly, we are creating a system where no one can take control. And if no one can take control, the system can never be stopped. Because there's no one to go to say, stop doing this. And one important thing to remember is that a smart contract isn't really a contract. It's not something that you go to a lawyer and draft up and then take to court if your counterparty doesn't follow the contract or doesn't follow through on the promises they make in the contract. A smart contract is designed to mimic the effect, the same effect that you would have if you actually had a legal contract that was enforced by courts and government. So it's a way of making sure people follow through with their promises without asking a court to help you with that. So you're enforcing the promises that they made without using force. So, for example, one of the earliest examples cited for an application of smart contracts is an ignition kill switch for a car. If you're borrowing money to buy a car, the bank will expect you to make regular payments on that car. But if you miss a payment, then the bank has to send some guy to come after you and repossess the car and take it away from you. And that's an expensive process, and it doesn't always work because you could just get in the car and drive away. So an automatic kill switch will disable the ignition of the car if you miss your payments. And that's an example of enforcing your obligation to make a payment without sending some guy to beat you up. So the point of a smart contract is not to be a contract, but to use technology as a substitute for legal contracts. Okay, so everyone here went to Martin's talk and the blockchain talk before that, I think. Does anyone here not know how a blockchain works yet? Okay, I'm going to go through this next section very fast. So I'm just going to give a brief history of distributed ledgers because they've been around for a really, really long time. So back in the 17th century, there was something called the British East India Company, and the British East India Company had colonies all around the world. They would send ships out to the East Indies, pick up tea, bring the tea and sell it in North America. They would go to Africa. And back then, everyone was on these slow-moving ships. It would take 6 months to make a trip out from London to the East Indies. And there weren't any telephones or computers. So the headquarters were in London. And the headquarters in London wanted to keep track of all the assets that were changing hands and all the sales and trades that were made in each of the colonies. But they had no way of doing that using modern technology. And to make matters worse, the ships out there, sometimes, there were a lot of pirates and enemy ships out in the ocean. So if you sent a ship out to the East Indies, that doesn't mean the ship would always come back. So it made it very difficult for the London headquarters to keep a ledger of everything that was going on. So what they did was they used a lot of replication. For every single ship carried an append-only record of the land ownership and production for every single colony they stopped at. So every ship basically had a full record of everything that was going on in the colonies all around the world. So even if one ship sank, another ship would make it back to London and they'd be able to figure out what was lost on the sunken ship. And because all the ships were sailing around in different parts of the world, there wasn't a lot of concern that the ship captains would collude and steal some treasure off the ships and fudge the records. If captains came back with records that were mismatched, they would get their heads cut off. So in this way, we have a distributed, replicated ledger, and it's fault tolerant and it's secure because everyone's centralized, and they were using double entry ledgers, which makes it hard to insert a fake entry in the middle of all the other entries. So we know how to build trust-minimized distributed database in the physical world, and the point of a blockchain is to bring this same effect into the digital world. On the internet, we have all the problems of the physical world and worse, because now it's easy to fake information online. You can send out fake news, you can set up bots that have fake ledgers, and information is easy to edit. And that's the problem that the blockchain is here to solve. And I'll go through this fairly quickly because you guys already all know how a blockchain works. So basically, you can think of the Bitcoin blockchain as a shared spreadsheet, except it's not just a shared spreadsheet because it's a spreadsheet that has to accommodate a very different threat model than if you were just sharing the spreadsheet with your friends. Your threat model now is your counterparty, the other people who are using the spreadsheet, and the government that might, or anyone who might try to seize your spreadsheet, and anyone else that might be coerced by the first two. So this is the threat model that we're using when we take a spreadsheet and multiply it over thousands of nodes around the world. Okay, so the Bitcoin blockchain consists of blocks that are linked together by hashes. Each block contains a hash of the previous block, so you know that a block can't be inserted into the middle of the chain. I guess everyone knows how a Merkle tree works. Each block contains a set of transactions, and the transactions are hashed together to create the root hash, which is included in the block header. In theory, the Bitcoin blockchain or a blockchain isn't new in that it uses hash trees because Even GitHub uses hash trees. What makes it really resilient is that it's decentralized. There have been many past attempts at creating digital money, but they were all shut down because they had a single point of failure. With Bitcoin, or with any blockchain, there are many nodes all around the world, and because there are so many decentralized nodes, shutting down one single node or the nodes in one single country won't stop the network. Okay, so you guys all know how the distributed ledger of Bitcoin works. Now, one thing with a spreadsheet, no one really uses a spreadsheet just for recording numbers. And a blockchain's ledgers don't have to be used only for recording numbers. You can put functions and calculations into a spreadsheet. And you can do the same thing with a blockchain ledger. So by performing calculations or functions on the spreadsheet, you can make programmable blockchain assets. So not only are we keeping a copy of the ledger on every single node, we're going to replicate the computation that's done on every single ledger. So the secret, or there's a secret with Bitcoin. There's not really any Bitcoins. No one actually owns any Bitcoin. The Bitcoin blockchain is just a transaction history. And the way a Bitcoin is spent isn't that you send a Bitcoin to someone else. It's that you sign a new entry in the ledger that assigns the Bitcoin to the next person. So, for example, Bitcoin is a double entry ledger, so every debit has a corresponding credit. And with every credit, there's going to be an encumbrance that tells you how you can spend the output. So, for example, right now we have Bitcoin transferred to Alice, who then transfers it to Bob. But I can't just come in and add my own entries that say Bob transfers it to me, because there's an encumbrance at each transaction output. And the encumbrance is just a function that has to be computed before the next entry can be added, referencing the first one. So the simplest encumbrance is just to check the signature. So at the output, or in order to spend the output, you enter the public key of the entry that you want to spend, and a signature that corresponds to the public key. And if the signature is valid, then the function returns true, and that enables the next entry to be added using referencing that output. So this is a scripting language that's used in Bitcoin transactions, and it functions as a very primitive type of smart contract. Checking a signature is not terribly interesting as far as smart contracts go, but you can also include an instruction to check multiple signatures. For example, if you want to create a transaction output that can only be spent if, say, 2 out of 3 key holders sign the transaction, then you can use the multi-sig instruction. And when you use a multi-sig that requires, say, 2 out of 3 key holders, then you can set up things like an escrow, where the 2 counterparties each have a key, and then a third person, the notary or the escrow, has the third key. And if there's a dispute, the person with the third key acts as the tiebreaker, because we need to get 2 out of 3 signatures for it to work. We can even go a little bit more complicated than the multi-signature transaction. We can create conditional functions. For example, if Alice has an account and Alice wants to let her friends, Bob and Charlie, spend the money in her account after some amount of time, if she hasn't spent it already, then you can have an if-else. So if Alice signs the account, or signs the transaction herself, and spends the money, then it's done. But if that doesn't happen, say after 3 months or some amount of time, then Bob and Charlie can both sign the transaction, and if both their signatures check out, then the transaction gets spent by these two inputs, or these two signatures, signing together. And you can have, and there are instructions where you can check the lock time to make sure that 3 months has actually passed. So this starts to get a little bit more complex, and in theory, once we're able to do if, then, else statements, we can create a state machine. But since Bitcoin script is a stack-based language and everything is evaluated on a single transaction, it's not very user-friendly to create complicated state machines. For one thing, a Bitcoin transaction can't actually store internal state. If Bob and Charlie are the two key holders for a multi-signature address, if Charlie submits his signature, but Bob has not, you can't enter a waiting state where you're waiting for Bob. Both of them have to submit their signatures at the same time, or else it doesn't work. It's sort of all or nothing. So each Bitcoin transaction can only represent a single state, and that's a little bit limiting in what it can do, because that means if two people are on a multi-signature address together, you can't remove one person and add another person, or cancel it, or whatever. You would have to move by repeating the same instructions over and over, but that's obviously not very efficient when it comes to creating a compact transaction. And then we talked about the lack of internal state. It's hard to make multi-stage scripts when the transaction itself can't hold state. And a third problem is that scripts can't access data beyond its own transaction, which makes it hard for a single Bitcoin the script inside a Bitcoin transaction can't really interact with other scripts. And one more limitation is that the values are predetermined. You can't dynamically assign output values because each ledger entry output has its own encumbrance. And the code, the script associated with each encumbrance can't be modified after it's in the blockchain. All right, so that brings us to why Ethereum came along. Bitcoin script is powerful for, or Bitcoin itself is powerful for acting as a very robust, resilient, distributed ledger. But for people who want to create more complex apps or programmable money, Ethereum is a lot more flexible. So Ethereum was designed for smart contracts, although I put the term smart or contracts in quotes because they're not really contracts. They just refer to applications that can control money. So you can think of the Bitcoin ledger as a state machine, whereas every time you modify or add an entry to the ledger, you're changing the current state. Each transaction ends up being like a state transition. So, for example, in this very first state, Alice has 100 Bitcoin. In the second state, Alice has sent or transferred her 100 Bitcoin to Bob, and we're now in the second state where Bob has 100 Bitcoin and Alice has nothing. If Bob then transfers his Bitcoin to Chuck, Debbie, and Elaine in 3 different outputs, then we have a third state where these 3 people have some amount of Bitcoin and Bob has nothing. So you can think of each ledger representation as a state machine. The set of credits available to each user constitutes a state. And in Bitcoin, this is called the unspent transaction outputs. So the state just looks like a bunch of account credits or unspent transactions. When you create a new transaction, that's a state transition to the next state, which has an updated view of which accounts have available credits and which accounts are authorized to spend or create further transactions. Ethereum looks very different as a state machine. It's not a double entry ledger, so it's more like a balance sheet where it keeps a list of users or account names and their corresponding balance and some corresponding information about each account. So in the first state, we have Alice with, say, 100 Ether. In the second state, Alice has sent 50 Ether to Bob, and her transaction count increases by 1. So in the next state, Alice sends another 25 to Chuck, and her transaction count increases to 2, and so on. So it's a balance sheet where every single time a transaction, or every time a transaction or set of transactions are mined into a block, then the state updates. So Ethereum is more intuitive as a state machine because, well, the state is already stored at each node. And the transactions in Ethereum look very similar to transactions in Bitcoin, where each set of transactions provides an update to the state or a state change. So, whereas Bitcoin transactions are basically ledger entries or programmable ledger entries with some instructions attached for how to spend the Bitcoin, Ethereum transactions are messages. So each Ethereum message has a recipient, a sender, but more importantly, the signature that identifies the sender. Each message has a value, which indicates the amount of Ether to transfer, and then some data in hexadecimal format, and something called gas, which we'll get to in the next 2 slides. So Ethereum doesn't send instructions along with the transaction the way that Bitcoin transactions do. With Ethereum, the intention is for the transactions to interact with the instructions already stored in smart contracts on the blockchain. So here are some examples of what a transaction might look like, and we'll go through this later on. So for example, you could do a simple transfer where Alice sends 5 Ether to Bob, and that just has a recipient, a sender, a value, and when this transaction is included in a block, the state is updated to reflect a transfer of 5 Ether. Another type of transaction is where you create a contract. So when a contract is created, what the sender does is send some compiled code to a blank recipient. And once the code is included as a transaction in the next block, then a new address will be created that references that code. And there are also transactions where that are sent to a contract directly. For example, if Alice is transferring tokens to Bob, she would be interacting with a token contract, so the recipient would be the token contract. And the data would be the instructions, send 5 tokens to Bob. So now instead of telling the blockchain to do this, Alice is sending the instructions to the smart contract, and then it's up to the smart contract to update the state. So in Ethereum, the universe, where the state of the universe is made up of accounts, and there are 2 types of accounts. One is the accounts that we think of when we think about using cryptocurrency. It's an account controlled by a private key that's probably controlled by a human. There are also contract accounts, where no one controls the contract except for itself. So if Genevieve here creates a contract deployment transaction where she sends compiled code out as a transaction, then it ends up, then the code is stored at the new contract address. And this code will control everything that happens at this account. And a contract account, and other than being controlled by code instead of a human with a private key, a contract account can function just like a regular human account. It can create transactions, it can send Ether to different people on the blockchain. A contract account can even create its own contract. So for example, if the code at this address had some instruction that said send a transaction that creates a new contract, then a new contract can be created by the first contract. So contracts can create contracts, and contracts can do all the things that humans can. A contract runs in the Ethereum virtual machine. So in Bitcoin, whereas a transaction would be validated by each node, an Ethereum transaction would actually run in the virtual machine. It's an isolated sandbox that runs the code of the smart contract. And smart contracts are typically written in a language called Solidity, which then compiles to machine code. And every single Ethereum node has the same virtual machine and will run the same contract code in the virtual machine to validate transactions. So for this reason, Ethereum is called the world computer, because these smart contracts are basically apps that simultaneously run on every single computer that's in the Ethereum network. And having an app or a smart contract run on thousands of different computers exactly the same way is really inefficient. And the reason why we do this is because having the same app running on thousands of computers makes it both fault tolerant and censorship resistant. I mean, the first thing that many people think of when they hear that permissionless apps are going to be run on virtual machines on computers all around the world is, well, how do we break this? I mean, what if someone puts in an infinite loop? If there's an infinite loop running on every single machine all around the world, or on every single machine in the Ethereum network, then that's going to grind Ethereum to a halt really fast, and it's not going to work anymore. So in Ethereum, there's something called gas, which limits how much or how many computations you can ask each virtual machine to do. So Ethereum, as I mentioned, is the smart contract code is typically written in a high-level language, but then it compiles down to machine code, and each instruction in that in the Ethereum virtual machine instruction set has a predefined amount of gas that it uses, and you can think of gas as CPU cycles. Like, how many CPU cycles will it take to run each instruction? And for every CPU cycle or gas that it consumes, the sender has to pay a fee. And in order to get the miners to include a transaction that performs a lot of calculations, the sender sets a gas price. So the gas cost is determined by what instructions you're asking the computer to perform, and a gas price is how much in Ether you're willing to pay for each gas or for each CPU cycle that's used. So over time, the price of gas has stayed fairly constant. So it's fairly predictable how much your transaction will cost based on the instructions that, or based on the code that needs to be run. And this is denominated in Ether. So the price of Ether has gone up a lot in US dollars, in fiat currency. So it looks like, if you put this in US dollars, it would look like the gas price went up by a lot. And one more thing about the Ethereum virtual machine. With Ethereum, a block is created every 15 seconds, and this is a lot faster than with Bitcoin, where a block is created roughly every 10 minutes. And because the state of all of Ethereum is updated every single block, it would be really inefficient to try to send the entire state database in each block. The way the state database is stored is something called a Merkle Patricia tree, where each branch represents that represents a key value store, and the path of each branch maps to the hex encoding of an address. So when a node is validating transactions, it runs, it processes the transaction, updates the state of the database, and then only updates the state root, or only includes the state root in the next block. This way, every single node that receives this block can run through the same computations based on the instructions, or based on the transactions and the smart contracts. And if they arrive at the same value for the state root, then they know that the block is valid. And if they don't get the same value for the state root, then they'll ignore the block. So even though the state database is actually a fairly large entity, it's not, the block sizes are actually fairly small because only the roots are being passed along. And the blocks also include the transactions, just like with Bitcoin. Okay, yeah, so the state database basically constitutes all of the accounts that exist on Ethereum, along with what's stored at each account. So for example, if there's code at the account, then the hash of the code will be included. There's data stored there, that will be included also, and the account balance, of course. One downside of having every single computer in the Ethereum network store the entire state database is that it starts taking up a lot of memory really fast. If you were to do a full sync of the state database on Ethereum, you'd end up taking up almost 350 gigabytes. The good news is, since Ethereum is a state machine and the state database is updated every block, it's not really necessary to keep track of the state information from earlier blocks. Typically with a blockchain, I mean, one of the biggest value adds of a blockchain is that you can trace transactions from the very first block to the very last one. With Ethereum, while ideally many nodes would store the entire state database to track state changes from one block to the next, you can prune you can prune blocks that are older than, or you can prune state snapshots that are older than a few weeks, and that lets you decrease the size of the database to about 15% of what it would be if you had the full database. Okay, so now the exciting part with Ethereum. I'll go through some of the sample applications that people look at to get started in Solidity and to give a sort of introduction to smart contracts and how they're used. So this is Solidity. You might notice that the syntax looks very similar to JavaScript. You create a contract with the word contract. This one is a simple storage contract where you just store an integer. There's a function that can be called that sets the integer value, and then there's another function that gets the value that was stored in the contract. And the way this contract works is it first gets sent to the blockchain, or it gets sent as a transaction where this code will now live at a given address on the blockchain. So let's say Alice wants to interact with this new contract. So she sends a transaction to the contract address, and she's the sender, and there's no value because she's not transferring money to the contract. She's just calling the set function. So this set function sets the stored data to the input, and the function or the set function or the data included in the transaction would look just like this. Set the number, except instead of looking like that, it would be encoded as hexadecimal. And if Bob wants to interact with the contract too, he can. The contract is on the blockchain where anyone can interact with it. He would create his own transaction to the contract address also, and he would have his data would say get, and that would also be encoded as hex, and it would return the value that's stored in the contract. So setting and getting a fixed integer is a pretty boring contract. So a more interesting one is if we create, say, a clubhouse on the blockchain. So this is a contract called club, and there are a few things to notice. There's a keyword called public, which means this information is accessible to anyone who interacts with the contract on the blockchain. And the other is there's a mapping. Oops. Okay, so the public variables are readable from the outside. And the mapping is actually a hash table. One thing with putting data on the blockchain is you can't resize a memory array after it's been created. So by creating a hash map, every single key already exists. And we're just mapping integer values to the addresses of members. And then, so for the very first function that we call this constructor, this is run on contract creation when it's first deployed to the blockchain. You can fetch the sender from the message, and message is a variable that's accessible to every contract based on who sent the message. And we set the 0th member to the sender of the message. So this person's creating a club and setting themselves as the president. And here's another function, add member. So you can call this function later on. And here it checks to see if the sender of the message, when add member is called, is equal to the president, because we set the president's address in on creation. So now when we want to add a member, we make sure we have the president stored. So we want to make sure the sender who's calling add member is the same person. And then we increase the index, which basically serves as a counter, and put the new member's address into the mapping. And you can do a lot of things with Solidity. Now, by using a keyword called payable, you can make any function capable of receiving money. So this is a new contract called fund. Let's say we want to start a crowd fund that receives money from people. Once again, you have the constructor, which creates the contract and sets the owner to the person who sent the contract. I mean, you don't have to set the owner to the sender, but easy to do. And we have a new function called pay dues. So if someone calls this function, the transaction can also include a value, meaning they're sending money to the contract. And then this contract is now in control of the ether that has been sent to it. And once again, we have this hash map, and we keep track of who has sent money by setting the balances of the sender to the value. And these balances are a globally, this is a public variable. And if you want to get the total funds that have been sent to this contract, you can call this .balance because it's referencing itself as a contract and getting the balance that's stored at the address of the contract, or the balance that the contract controls. So as mentioned before, a contract is basically just another type of account. And since a contract is not different, basically functions like an account, a contract can create another contract. So if this contract over here wanted to create a contract, it would create the same type of transaction that a human would create. And the data would be a compiled contract, just like if a person tried to send the compiled contract to deploy the contract. So for an example of when you might want to do this is if you had the club as a contract and you wanted to create that payable contract, the fund contract from the club. So you instantiate the club again, and within the club, within one of the club functions, you can instantiate the contract called fund. So when this new fund statement is made, that basically creates a transaction that creates a second contract that's controlled by this first contract. So here we have club instantiating a fund object, and it's stored in this Treasury variable that's public in the club. So just see how this chain of command goes. Originally we had Alice, who has a private key to control her own address. And she used her private key to control her address and create a contract at the club address. So her address controls this club address, which was used to create a contract at the Treasury address. So a human can create a contract, can create another contract. And on the blockchain, any one of these accounts can interact with each other. So the Treasury that was created by the club can send money to Alice, or Alice can send money to the Treasury, or the Treasury can interact with the club back, or send money to the club. So any of these can interact with each other because they're all on the blockchain together. Even though this one was created by a person, and this one was created by another contract. So to see what that might look like, you can add a, say, vote for president function in the club, and it can check the Treasury to see if the balance of the sender is sufficient. Like if that sender has paid their dues, then let them continue, otherwise return. And you can also create a transfer balance function that calls the Treasury and tells it to transfer money to the club president. So you have contracts interacting with other contracts. And I'll go through some of the most popular examples of apps that people are building on Ethereum. One is the multi-signature wallet. I mean, we saw this with Bitcoin. It's fairly simple. You have a wallet that requires, say, 2 out of 3 signatures in order to send a transaction. And we saw that with Bitcoin, you needed all of your signers. Like, if it was a 2 out of 3 wallet, you would require both signatures to send the transaction. With Ethereum, since contracts have internal state, you can have one person submit a transaction and wait until the next person submits their, or you can have one person submit their signature, or you can have someone submit a transaction. Then you can have each key holder confirm the transaction separately. So you can require multiple transactions before the payment is actually sent. And because it keeps track of internal state and can update stored variables, you can do things like add another owner to the wallet or remove an owner without destroying the wallet and creating a new one. You guys have probably heard about tokens, which is the most popular app on Ethereum right now. A token is basically a way to raise money. A token contract is an app that manages a balance sheet of who sends Ether to it. And when a person sends Ether to this token contract, a token is assigned to that person's address. And supposedly each token maps to some underlying asset. And what makes tokens so popular is previously people could raise money for projects and get credit for, investors could get credit for contributing to the project, but it wasn't possible for the investor to quickly transfer their ownership of the project. So tokens make it so, tokens have an important function called transfer. So if you buy a token or send Ether and have a token assigned to you, you can transfer it to someone else, which means you can buy the token when it's at a low price, tell everyone that the token is awesome and going to go up in price, and then sell it for a much higher amount. So people are pretty excited about tokens for that reason. Another popular app is a title registry. Right now, if you set up a website and want to register a new domain name, you go through a registrar like GoDaddy or 1&1. But you can register names on the blockchain. And Ethereum Name Service is a registry where you can enter whatever name you want and have it mapped to a contract address. So people don't have to remember a hexadecimal string. They can just remember the custom name that you chose. And this is basically just a key value store. And finally, data feeds make most apps possible. Right now, in general, on the Ethereum blockchain, the contracts can all interact with each other, but the contracts can't interact with anything from the outside world. For example, if you have a contract that is basically betting on the US dollar price of Bitcoin, you can't ping CoinMarketCap to get a price quote. Or if you're doing a stock trading app, you can't ping the stock exchange for price quotes. So an oracle is basically a relay. It's the same storage contract that we saw as the very first example, where you just set a value and get a value. And the person who sets the value is basically the person who is the interface between the outside world and the blockchain. And by continuously updating these values, other people or other contracts can use this contract as a price reference, and then you can start building things like stock markets or options. And it's easy to get started. Here are a few examples of interfaces that people use. One is called MetaMask. It's a browser extension. Another is MyEtherWallet. It's just a web interface where you can interact or deploy contracts with just a few clicks, as long as you have an account. And then there's Mist, which is a browser that with a graphical user interface, and you can also create and interact with contracts here. So one reason why Ethereum is so popular right now, even though Bitcoin could do smart contracts, Ethereum really took it to the next level and made it very user-friendly. So anyone can create an Ethereum account and start interacting with contracts with real money. And part of what Ethereum did was maybe they made it a little too easy, because if you follow Ethereum at all, every couple weeks or so you'll see a headline about how someone got hacked and lost a bunch of money. And that happens a lot. As you saw with the smart contract examples that we went through, the code looks a lot like JavaScript. So a lot of new developers come in and think, okay, this is just like web development, and they're kind of careless with their code. Because when you make a mistake with JavaScript on a web page, nothing really bad happens. But when you put a bug in a smart contract, I mean, it's on the blockchain, and once it's controlling money, you can't just stop it. So a lot of smart contracts have had bugs where the money somehow gets locked in the contract forever because they forget to put a withdraw function. The other thing is, with Ethereum's Turing complete instruction set, you can do a lot more things than you can do with, say, Bitcoin script. And that's not always a good thing. Being able to do more things means you have more room to make mistakes. And one thing that people often forget is that when a contract is on the blockchain, anyone can interact with it. Even if you make a smart contract that's just a betting game for you and your friends, if it has a bug in it and some stranger on the internet finds that bug, they'll exploit your contract and try to take money out of it. So that's something that happened about a year and a half ago when a smart contract was controlling something like $150, $160 million. Last summer it got hacked, and something like $60 million was taken out of it. So Ethereum actually did a hard fork where they created an alternate version of Ethereum that took the money back from the hacker, which is kind of cheating. But a lot of people lost money, so most people moved over. And finally, you hear a lot about financial institutions and banks that are really excited about smart contracts. And the reason for that is that this is what transaction process or post-trade processing looks like on the back of most banks. So they're really excited about blockchain and smart contracts because they hope to automate all this workflow. And finally, some other applications of smart contracts. Gambling's popular, crowdfunding tokens have been really popular. Then there's you can set up clubs with voting, decentralized organizations and markets. And right now, Ethereum is only 4 years old, or 3 years old. And there's still a lot you can do with it. And the best applications are still waiting to be discovered. It's still very new. People are still exploring and figuring out where the boundaries are. So here are some references that can help you out if you want to explore this for yourself. And thanks. But I'll go back to that because that's probably more important.